This is the last setup video, and thanks for your patience while I go through all this setup work before we actually get back to differential equations. I'm going to want to use the Laplace transforms to change a differential equation into a normal equation. Then I want to solve the normal equation. However, after doing that, I do need to get back to the t-domain, to the original functions. The solution shouldn't be a function of s, it should be a function of t. Therefore, I have to undo the Laplace transform after I'm done doing whatever I need to do in the s domain. I need the inverse transform. And that's going to be written in script L with a -1, as you might expect. And it will be something that undoes the transform, that gives me back the original functions. There is a deep theory of transforms and their inverses. I'll only touch on that very lightly here, since the machinery for that theory is beyond this course. And in particular, it needs the calculus of complex numbers and the integrals of complex number functions. This is the formal definition. The inverse is a complex number integral over a certain path in the complex plane. It looks very much like the original transform, but with a positive exponential instead of a -1. But unfortunately, doing this just sort of naively doesn't give the inverse transform. Instead, it needs a bunch of extra steps and complex numbers. That is, again, beyond this course, so this definition, as interesting as it is, isn't going to be something that we can use directly. So what do we do instead? Well, what we do is actually pretty simple. We make a list of all the Laplace transforms we've done so far, and we just reverse them by matching. The first 5 equations here are just the reverse of Laplace transforms from the first few videos this week. To do reverse transforms, I just have to recognize these patterns and go backwards. Here are 4 more patterns for you to consider. You could calculate these Laplace transforms if you wish, but I'll give them to you here. The reference materials also have a bunch of tables of Laplace transforms. I haven't proved these, but they can all be proved by taking the transform of the t function and by producing the s function by calculating the integral. I'm just reversing these specific examples for you. I'm including these patterns for you because these are the particular expressions that tend to show up in the applications in the solving of differential equations. There will be some very specific patterns to look for. If I multiply by an exponential in the s domain, it turns into a step function and a shift in the t domain, which we talked about a couple of videos. And likewise, if I have something that is a derivative in one of these patterns, I can also get back to the t domain using the derivative rule in the s domain. Between all these tricks and patterns, we should be able to undo all the transforms that we come up with in the solution of differential equations. And then again, that's all there is to this video. This is another pretty short one. To undo transforms is just to look for these patterns and then go backwards. It can be tricky to find the patterns with all the shifts and derivatives and complexity, but it's still just pattern recognition, and in the future videos, I'll work through a bunch of examples to demonstrate sort of how this pattern recognition works. And finally, this is the end of the setup. We now have all the tools we need, so in the next video, I'll finally start solving some differential equations using Laplace transforms.